So after the introduction, speaking about the importance of the red giants in the revolution of astroseismology, I will speak about the possibility to study a lot of stars at the same time. So you see here the chart diagram with the pulsators that there is all in the main sequence and post-main sequence. And you will show all these variables during these days, but I will speak mainly on this part of the diagram, that is solar-like oscillators, that they have periods that change from minutes to hours. They are excited by they are excited by convection that is in their envelope. They are also damped. The amplitudes, they are small, depending on the evolution, but they go from ppm to tens of ppm. They present acoustic modes, radial and non-radial. This was the novelty. And in the subgiant and giants, we have, in addition to acoustic modes, also PG modes, mixed modes that have the possibility to sound the interior and external part of the star. And that was the situation before CoRoT and Kepler. That was the solar-like oscillator that was detected after a lot of work. And you see here, that is not the people who discovered or observed this star. It was the people that has published things about these stars. Many people for so a small number. And that is the situation after Kepler and CoRoT. You have here the chart diagram with the oscillators in observing the field of Kepler, and here those in CoRoT. And you see the numbers. We have 500 dwarfs and subgiants in Kepler's field, and several thousands of giants. And on the other hand, in CoRoT, we have also a lot of red giants in the exofield, and some bright giants and solar-like stars in the seismofield, so brighter stars. So we have all these stars that present all of them more or less the same behavior. That means the power spectrum presents this shape, like that of the sun. It presents one comb-like spectrum. That means that we have the acoustic mode or the radial mode equally spaced by one quantity, that is what we call the large frequency separation. That is, there is one error, is DR sur C, sur the sound speed. That is two times the time that the perturbation takes to go through the star. And it's usually said that it's equivalent to the square root of the main density of the star. We will see after about this. The power spectrum presents one Gaussian shape with the center at one frequency we call nu max, that is related to the frequency of cutoff. And we can relate it for an isothermal atmosphere to the ratio between the gravity and the temperature, effective temperature, the square root of it. So that is what we call the basic scaling laws. There is also other scaling laws that relate the luminosity and the mass, and they are more important to study the energy of the modes, the excitation, the characteristics of the interaction between the pulsation and the convection, but I will not speak here about that. So, what it was interesting also from this studies, and they are expected, they behave exactly as you expect from their radius or the main density. And you see that as we go from the dwarfs, very dense here, And after we evolve with the radius that increase, the density decrease, and we see how the spectrum, the frequency of maximum of the spectra change with the evolution. It is exactly what we expect from the ratio between the gravity and the effective temperature, that it is in fact the radius who dominate. That is for the stars that are in this part of the HR diagram. And I speak also only before about the scaling relations concerning, if you want, the radial modes. But this star presents also non-radial modes. And there is a asymptotic relation that allows us to express the frequency mode, non-radial mode, as some function of the main large separation with the quality of equispacement. But there is also another quantity here that makes that for this mode, the distance between different L's is not the same. So this quantity here, we can write it as the derivative of the sound speed near the center. It's especially important that its contribution near the center. And is this the separation that you see here between one radial mode, one quadruple mode, for example. And that is, for the star, that is not very evolved. But as the star evolves, and there is one increase of the density contrast between the envelope and the center, the star increases the radius at the same time that the core contracts. That makes change the properties of the propagation cavities inside the star. And what happens is we will see to appear what we call a mixed mode first, at the beginning and at the end of the main sequence. And after that, when the density is in the center is really big, we see that the frequency of the gravity mode, that is smaller than that of the acoustic mode, are right at in the domain where the acoustic mode propagates. What happens is we see in the same domain of frequencies P modes, acoustic modes, and also gravity modes. And the gravity modes behave, on the other hand, showing one equidistance in period instead of in frequency. And the quantity of this equidistance in period, it also depends on the density in the central part of the star. So both from the small separation and from the period spacing for various evolved stars, we have one indication about the density contrast between the envelope and the center. And that is one sign of the evolutionary state and so on the age. And if we continue the evolution of the star from in the red diamond branch, we see that the new mass continue to decrease, but we see also, if you remember the previous plot, that the spectra also increase in complexity. We see that appears a lot of modes between what we call the acoustic ones. So what is surprising is we are able, seeing this power spectra, we are able to see exactly what is happening in the star. From the beginning, where the star is more or less homogeneous, after when it begins to contract the core, at this moment, the envelope and the core evolves in the one contract, other expands, and increase the difference between the properties in the one and the other. The two cavities are more and more uncoupled, and we recover one situation more or less as when we have one simple star in the main sequence. And after that, when the star evolves again and recovers another situation with another structure that corresponds to the nuclear reaction that begins in the center, we recover one sign of what is happening in the interior of the star. So we have all this information of a lot of this star. We have information on the main density and also on the density contrast that in fact is one indication of the evolution of the star. So what we can do with that? First of all, from the two basic scaling relation, we have the possibility to derive. Once we have delta nu max plus the effective temperature, we can derive the radius and the mass. And you have seen that we are able to have the radius and the mass for one big quantity of stars that are in the field. They are not binaries, they are not in clusters, and that is in fact almost incredible to be able to derive stellar parameters for this kind of targets. In fact, when we want to do that, we use clusters, we use binaries, but it's not possible to do it in the field. But with these parameters, what we can do a lot of things. First of all, as I told you, to have mass and radius for one enormous quantity of stars in the field is one gold mean, if you want, for study the stellar physics and also galactic evolution. We can, of course, derive the parameters of the planets. And there is one very basic thing. We can derive the gravity of the stars at the surface. That is one very important data for the people who do spectroscopy, because there is some degeneracy between effective temperature and gravity when they do the analysis of their spectra. And using the gravity from seismology that is much more precise, they are able to improve their derivation about the atmosphere parameters. That is one of the reasons why we finally have a lot of success with the people who do spectroscopic surveys, large spectroscopic surveys. We provide them the log G, and they will provide us with the composition of the star, for example. We can also do a study of stellar population, both simple, for example, and cluster, or one composite stellar population, like, for example, the Milky Way or the disk of the Milky Way. We can discriminate between members and non-members of clusters, because they have to follow the isochron. They have to, or the stars must have the same age, and we can only from the velocities in the field, we are not able to do it so clearly. It's possible, since we are able to derive the mass, we can obtain estimation of the mass loss. That is one data very uncertain in the field. There is parameterized, and we don't know. There is not a lot of constraint. And finally, we have also the possibility to use this data as distance indicators. I mean, we have the radius, we have the effective temperature, we have the luminosity, and so we have the distance of the star. And again, before Gaia, we will be able to have one estimation of distance that is not, again, is not possible to obtain for stars in the field. Also, only in a cluster or in binaries, for example. One quantity that is very interesting for all of us is the age of the stars, in order to study the evolution of the stars, the evolution of the planetary systems, of the evolution of the galaxy. And one possibility that gave us the red giants is to derive the age from the mass, because it's one good proxy of the age. But it still is a little model dependent. It's model dependent, but not so much as for the dwarfs. in fact, you have here what is the dependence of the age of the red giants as a function of the mass. For different, the color indicates the chemical composition. And you see here that for 1.5 solar masses, you can estimate the age between 9 in log, 9.3, 9.5, more or less. But if you know and you see that follow one very tiny relation. And if we add the knowledge of the chemical composition, we reduce the uncertainty on the age until 15%. So again, to have this information to study the evolution of the formation and evolution of the galaxy using the red giants is one of the objectives that we have and in the groups in which we work in the red giants. By comparison, you have the same thing here, but for the stars in the main sequence. You see that there is one large discrepancy or uncertainty in the mass. In the age, because during the main sequence there is a lot of factors that influence the determination of age. In particular, the mixing processes that we don't know how they work and how much important they are. Let's say we can constrain the mass loss. Usually, you use one law, empirical law, HERMES, and using the stars in the cluster, the stars that are in the RGB and in the red clump, and estimating the mass in the RGB and the mass in the red clump, we can see the difference between the one and the other, and so to have an idea of the integrate mass loss during the red giant branch evolution. So the possibility, what I told you, it was the possibility to do studies of stellar populations. And what you see here are the stars located in the galaxy, over the plane and on the disk. And you have here different colors for different runs of CoRoT, and also the green one corresponds to Kepler. And with the first runs, for which we have around 2,000 red giants with seismology, we was able to use this data to derive mass and radius, and doing simulation to estimate what are the distribution of mass and radius in one side and the other of the galaxy, in the center and the anti-center. And what it results is that we have one difference in the distribution of mass in both sides, and so it indicates also one difference on age. Nevertheless, I have to say that here we have also the estimation that we do on the age. We have to do simulation because we don't have an idea for the moment about the ages of this star, because first of all, we don't have the chemical composition. And and in this moment, we didn't have also the evolutionary state. So we have, I told you, one series of things that we are able to derive using only this very simple scaling relation. But the problem is they are true, or they are true in which range. So one possibility to study if these relations are good or not is, first of all, to derive the large separation, for example, from models, from frequencies, and compare to see if, in fact, that gives us the main density or not. Another possibility is to do independent measurements of radius and mass. As I told you, that there is one limited range of situations in which we are able to do that, so clusters, binaries. And for the first for the first test, the models, what I show you here is the comparison between what the simple scaling relation tells us about the main density and as a function of the new mass, so of the evolution of the star for different masses, from low mass, 0.7 until 2.4, during the RGB, and during the central helium burning phase, so the red clamp. And what we see here, first of all, is that there is even during the RGB, they don't follow the line equal 1. That will mean that we have that delta nu is in fact a good estimation of the mean density. But we have also that the difference depends on the mass, depends on the evolutionary state. Inside the evolutionary state depends also on the mass. And if we do the same computation with different chemical composition, we obtain here the data corresponding to one metallicity 10 times smaller than the solar one. And we see that it depends in the mass, in the stellar, in the evolutionary state, and also in the chemical composition. So we have to take all this into account in order to exploit the data that we have. We have also the possibility to test for example, the radius in the mass and the mass, and using nearby targets that are known, or using interferometry, using parallax for the sum of stars that are known, and use the stars in the cluster observed by Kepler. Doing all these kind of things, we arrived to one agreement for the radius in the order of 4%. And for the mass, it's not so good, it's 10%. And there is also one systematics in what I understood from the eclipsing binaries, is that overestimate always the mass with seismology with respect to what gives us the binaries. But nevertheless, it's not so bad. So mass and radius are not so bad. But what about the age? How I thought before that the age depends on the models, and the more important things are first the mix in the core, the mixing processes, and also the evolutionary state. And I show you here only what is the density distribution when we do one study of the population in order to identify the age of one star. If we don't know the evolutionary state of the star, we have two peaks, and nevertheless it's very large, the domain of data. So it's important to know the evolutionary state. And what I show you here is that from non-radial modes, so from the small separation that I showed you before, that behaves differently in the RGB, like here, for 1 solar mass, and here for 1.5. That in the helium burning phase, what you have here the behavior, and you see, for example, for 1 solar mass, there is one difference between this position and this one, concerning at the same separation, concerning the value of the small separation of 0.1. So again, I recall you that the small separation depends on the central density, on the density contrast. And so we can use the small separation from between radial and quadrupolar modes to estimate or to discriminate the evolutionary state. There is also the possibility to estimate the evolutionary state from the period spacing of dipole modes. As I told you before, that in these phases appears the gravity modes, so the mixed PULSATION gravity modes, that they have to show one separation that depends on the concentration density contrast in the star. And the density contrast changes when we are between the phase where we have in the RGB where the core is very, very, very dense, is degenerate, and the phase in which we are burning the helium. And we are able, that are the results from Kepler, and we are able to discriminate between the two situations, and that is the more recent result. So we have the possibility with dipole modes and also with quadrupole modes. And also from the non-radial mixed mode, we are able to estimate properties about the mixing in the star. And there is one relation, or a scale relation, if you want, between the period spacing and the mass of the helium core. And this relation that you saw here is the same with we use overshooting or not during the main sequence. And we know the mass from the region, we know the period spacing, and so we know the star that is here, what is the mass. And the mass that we have in this position, in the minimum mass of the helium core to begin the helium burning phase, is only determined by what is the mixing during the main sequence. So from data in the post-main sequence, we are able to derive the data in the main sequence. And also, from the period spacing, we can derive the site of the convective core during the helium burning phase. So the scaling relations have an enormous potential, in particular for the study of stellar population. But we need to calibrate them, these relations, for example, with binaries, for example, with parallaxes. The parallax will tell us something if the relation with the radius is good or not. And here I show you what is the expectation for Gaia for the magnitude of the radii we have in CoRoT field. And so we see that depending on the distance, we are able to have the distance with the parallax with quite good uncertainty. And one thing that appears several times in this presentation is the need to have the metallicity, the chemical composition to exploit really this data. And that we will have it thanks to the collaboration with large spectroscopic surveys like APOGEE, Gaia ESO survey, and GALAH HERMES. All of them has begun already to observe both CoRoT and Kepler stars.
Thank you.
Thank you very much.
So we have a time for one or two questions, depending on the length. So.
I just wanted to make a comment on your diagram using models to test large separation against mean density. I did that calculation several years ago using your models, right, from your website, and I got a much larger spread, particularly for low Z, which I think is 0.006 in your lowest case, and masses up to 1.5, up to 20%.
But it was, sorry, but it was only main sequence model what I have in the...
Yeah, sure. So
okay.
I tested with main sequence models, and it went up to 20% for the largest mass, lowest density, and the largest mass was 1.5 that I used. So I got a bigger scatter than you did, much bigger.
For the main sequence?
Yes.
Yes?